So, last time you recall we were talking about the master equation for Markov processes, and just to refresh you your memory, we said consider a conditional probability density that the system is in state some state k at time t given that it was at j at time 0 and this quantity, this set of quantities obeyed a set of coupled differential equations which was of the form d over dt of this was equal to, on the right hand side you had a summation over all possible intermediate states. So, L equal to 1 to n W k L P of L T j minus W of L k P of k T given j. Okay. And these quantities were the transition rates to go from the state L to the state K. Okay. And there was a constraint here which said that L not equal to K. Yes. And this is what I call the master equation. It is a coupled set of first order differential equations for this quantity, and of course the initial condition could be anything you care to specify. Since we are talking about conditional probabilities, the initial condition is P of k 0 j equal to delta k j. Okay. So, the task is to solve this set of equations given that initial condition, and then you have a whole host of probabilities. Okay. Now, notice that I rewrote this as I wrote a column vector. So, I said let P of t be a column vector with elements P of 1 t for each j etc. up to P of n t j in this fashion, and then this equation became dP of t over dt equal to a matrix W acting on P of t. And this matrix W, as you can easily verify, has the following elements: W kj equal to W kj for all k not equal to j, all off diagonal elements were of this form, and the diagonal elements Wkk was equal to minus the sum of all the other elements in that row. Okay. So, this is equal to W for a given k, if k is 1 for example, it is W 2 1 3 1 etc. etc. So, it is W L k summed over L equal to 1 to n, L not equal to k. Okay. So, we have this picture of a matrix where each column, each row adds up to 0. Okay. So, the determinant of W is 0. Now, W has real elements, all the off diagonal elements are either 0 or positive, and the diagonal elements are all negative. Just go back to this equation. Let us write this equation for instance for the case when k is 1, okay, and let us suppress the index j, that is not necessary here. So, essentially you have an equation like d over dt p of 1 comma t equal to, on the right hand side you have to sum over all k 2 3 4 etc. etc. So, it is equal to W 1 2 p of 2t plus dot 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 plus W n sorry, I put k equal to 1. So, 1 n P of n comma t minus this quantity here which is just a sum over L leaving out the index 1. So this is equal to minus W 2 1 plus W 2 3 plus etc. times P of 1 comma T in this fashion, right. And this is what I call W12, capital W. So it is clear that all the off diagonal elements of this big matrix W are precisely W12, W23 and so on and so forth, multiplying P2, P3 etc. column vector. And what multiplies P1, because after all what does this equation imply? It says P of 1t dot 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 P of nt, the d over dt of that equal to W times P. So that is W1 P of 1t plus W12 P of 2t plus dot 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 etc. on the first column, and then similarly for the other guys. Okay. So dP1 by dt is this fellow here, and W11 as you can see is minus of all these, just writing this out explicitly. Okay. So the important thing to remember is that the off diagonal elements of W are the transition probabilities, transition rates, and they are non-negative, they are either 0 or positive. Okay. If two states are not directly connected, then that particular W happens to be 0. Okay. We are making some assumptions here which I have not technical assumptions about the nature of this W matrix. We will talk about it later on when I give you special cases of it. There could be situations where we are talking about the generic case. In other words, we are talking about a Markov process in which you can reach any state from any state, no matter where you start. There are no subsets of states which are closed among themselves and so on. So we are taking the general case where all the W's exist and then you have transitions possible. Now you must remember that it is entirely possible that you may not be able to go from say state 6 to state 8 directly. There may be a 0 transition probability, but given enough time you may go from 6 to some other state 5 and then 5 to 8 and so on. So that possibility exists, of course, right? And that is really what happens most of the time, because we will look at cases where you may be able to jump only from a given state to neighboring states on either side, and yet over a period of time the system wherever you start will reach any other state. Okay, so we have this W matrix, and then we wrote down a formal solution to it. And that was just the exponential of this matrix W. So we had d over dt P of t equal to W times P of t, and this implied that P of t was e to the Wt is equal to e to the Wt times P of 0, whatever that is. And in the case we are talking about, this P of 0 is a column vector in which the elements are all 0 except for the jth row which has got 1, because you are starting with the state j. Okay. So the task reduces to finding this quantity here, and the statement made was, what sort of time dependence can we generically expect? And the answer is, you expect things to decay in time to some equilibrium distribution, and we already know what that distribution is. We have some idea of what it is, because remember that determinant W equal to 0 implies lambda equal to 0 is an eigenvalue of W. You can actually prove more than this. You can show that the 0 is a simple eigenvalue, that is not a repeated eigenvalue generically. Moreover, that it has a right eigenvector which will be the stationary probability distribution, and in the simplest cases we are looking at, it is a unique vector. What is important is when you are going to identify the elements of this eigenvector as corresponding to probabilities, we better make sure that the elements can't be negative. Okay. So we need a guarantee that this eigenvector has elements which are not only real but also have are also non-negative. Okay. There are theorems which assure us of that. So one of them was the statement I made that the eigenvalues of this W can never have positive real part, and the reason I said was due to this disk theorem, which said that if you give me a general matrix M, and this was the famous Gershgorin disk or circle theorem, and what it says is if you give me an n by n matrix M, then take its diagonal elements and mark those points in the complex plane and take the sum of the moduli of all the off diagonal elements in that row, add them all up and draw a circle about this center point of that radius, and the eigenvalues are guaranteed to remain inside these or on these disks. That was the statement. This is not a hard theorem to prove, because look at it, here is a simple way of doing this. Suppose lambda is an eigenvalue, then it says m times some eigenvector u equal to lambda times u. Okay. Now let us look at a particular eigenvalue lambda, and let us look at a corresponding eigenvalue lambda and corresponding eigenvector u. Then suppose this u is of the form u1, u2 etc., and let us say the kth element in it is the largest in magnitude. Okay. So this fellow has elements u1, u2 up to un, and let us suppose that some element k, this fellow, has the largest magnitude in magnitude over all these elements. Then if you write this element down, it is clear that m kj uj must be equal to lambda times uk. I write this down for that element out here, and there is a summation over j running from 1 to n. So let us take out the j equal to k element and put it on the right hand side, and then it says summation j equal to 1 to n, j not equal to k, m kj uj equal to lambda minus m kk on uk. Okay. Now take modulus on both sides, then it immediately tells you that modulus of lambda minus m kk times modulus of uk, I will transfer it to the right hand side, equal to summation j not equal to k summed over j m kj uj over uk modulus. But of course this is less than or equal to summation j not equal to k modulus m kj times the modulus of this. Because if I take the modulus inside the summation, I get maximize the sum itself. But these numbers are guaranteed to be less than or equal to 1, because we took this to be the largest, right. So this is less than equal to summation j not equal to k modulus m kj. Okay. That is the disk theorem, because it says this eigenvalue is inside or on a circle of radius mkk, whose radius is given by this out here. So this region is a disk, and you are guaranteed the eigenvalues inside or on that disk. Okay. So all the eigenvalues of this M are either in or on the union of all these disks, all the Gershgorin disks. Okay. There are further refinements to this. For example, if one of the disks is disjoint, you can show that that disk has at least one eigenvalue, etc. Definitely has an eigenvalue, and so on. Okay. Now what we need is just one part of this theorem applied to this matrix W. Remember that we had this W whose off diagonal elements jk were all W jk, these guys were all positive numbers, and the diagonal element k was equal to minus summation j not equal to k w j k. Okay. So that immediately tells us that 0 is an eigenvalue in the eigenvalue plane, and all these numbers, the diagonal elements, are all at negative values because these are non-negative numbers inside here. So this is equal to minus modulus wkk. And so you immediately know that the centers are all sitting here and the discs look like this. Each disc looks like that. It touches 0. Okay. Therefore, the real part of lambda less than equal to 0 for all So the eigenvalues are such that e to the minus lambda t must decay to 0 except for the 0 eigenvalue where it remains at 0, there is no t dependence at all. Okay. Therefore, W is a relaxation matrix, things relax to the equilibrium state. Okay. And what is that given by? Well, the stationary distribution is not difficult to write down. So the stationary distribution corresponding to lambda equal to 0 satisfies P W d, of course it satisfies dP stationary over dt equal to 0, which must be equal to W times P stationary. So it is the right eigenvector corresponding to the 0 eigenvalue of W. Since each column of W adds up to 0, it is immediately clear that the uniform uniform row vector is an eigenvector, a left eigenvector, 1 1 1 1 1 etc. But this is not a symmetric matrix, so the left and right eigenvectors need not be the same in general, and the right eigenvector is indeed the equilibrium distribution, the stationary distribution. Okay, is that clear? Now how do we find it? Well, you need to put in this condition and discover what it is. So let us put that in, and if I write out what W is, and let us call this P of P stationary P1, P2 up to Pn. It is stationary, there is no time dependence, so I will not put in a t index at all, there is no t dependence in this. It is the single time probability independent of t, right. And what is that given by? Well, we have summation L running from 1 to n, L not equal to k, W k L, P of L minus W L k, P of k must be equal to 0 for the stationary distribution. Again it is a coupled set of equations, simultaneous equations, linear in all these fellows. Is there a guarantee that this will have a non-trivial solution? It is a set of homogeneous equations, and when does a set of simultaneous homogeneous equations have a non-trivial solution? When the determinant is 0, which indeed it is, we know determinant W is 0, right. So it has got a solution, right, it has got a unique solution, and you need to find that by solving this set of equations here, whatever it be. Okay. So this problem reduces to an algebraic problem, nothing more than that. So this thing will lead you to implies you can find this quantity explicitly. Okay. Now there are some important cases where you can write the solution down explicitly. Remember it is this sum that is 0, summed over L, but you could ask what happens if each of these terms is 0 inside the sum, okay, then you get a very special kind of distribution, okay, which corresponds to saying that term by term this sum is 0, and that is called detail balance. So since it is so important in physical applications, let me write it down. It is called detail balance. Implies that this quantity WKL P of L equal to WLK P of K for each KL K naught. Okay. For every pair this is true pairwise, and of course if that condition is true, then immediately you know that this that is going to give you the stationary distribution without doing much solution at all. And what is this actually saying? It says you wait for a long time, get to the stationary distribution, let P of K be the probability that you are in state K, then that multiplied by the transition probability rate that you go from K to L must be same thing in the reverse order. So here is the initial state, here is the final state. If you interchange the two, you get just this guy here. So the flow both ways pairwise is exactly the same, the weighted flow of probability mass. Now this would be a curiosity, just a curiosity, except for the fact that systems in thermodynamic equilibrium, physical systems satisfy detail balance, provided the underlying dynamics has a property called time reversal invariance. I will not get further into the details of this at the moment, but just to tell you that it is a very, very important special case. There are lots of physical systems under very general conditions which satisfy detail balance, in which case this thing is immediately true. And what will that tell us? It gives us the ratios of all these probabilities. So you choose any one of them, say P1, then you can find P2, P3 and so on in terms of this P1. And how would you determine P1 itself? You normalize the probability. Remember, you have to normalize, right? So remember that you definitely need this summation k equal to 1 to n, P of k must be equal to 1. Okay. So we know all the ratios P2 over P1, P3 over P1 up to Pn over P1, and we know P1 itself from that set of equations, provided you have a normalization condition. There has got to be one inhomogeneous condition, which is what this is, and with this normalization you can find all of these fellows. I leave it to you as an exercise to show that in the general case for arbitrary n, when you have this detail balance condition valid, then this will imply that the solution P of k looks like this. It looks like 1 over, and this is a well known form, so it is worth memorizing it, 1 plus a summation L not equal to k 1 to n, a ratio I like you to verify this. Okay. So there is a very simple formula, essentially an algebraic formula for the stationary probability distribution of this Markov process, in the stationary Markov process in the case when detail balance is valid, okay. And then it is just that simple algebraic formula out there. What happens if the rates are all the same? The rate from L to K is the same as the rate from K to L. What do you think would happen? Now you are saying not only detail balance, you are saying that look, this rate is equal to that rate. That tells us this must be equal to that. The probabilities distribution must be a uniform distribution. There are n states, you are in the steady state and each of them is equally probable. So what is the probability of any one of them? 1 over n, and indeed that is true, because if these rates are all equal, this cancels, gives you 1. There is a summation here except for one index k, so this is n minus 1, you add it to 1 and you get a 1 over n, okay. So this goes over But when you do not have that, extra condition that the transition rates are also equal, then of course you have a non-trivial solution in terms of all the transition rates. Okay. Now let us look at the simplest case. The simplest possible case is when you have just two states possible, and this is such a famous case and it applies in so many places, it occurs in so many places that it has got a special name to itself. It is called the dichotomous stationary dichotomous Markov process. Corresponds to n equal to 2, just two possible states. We can write down what the solution is in this case, because the stationary distribution is utterly trivial in this case. You have summation over L, and for any given k it runs over only one other value for 1 or 2, right. So L, k, etc. run over values 1 to 2, and you have W for the stationary distribution, you have W say 1, 2, P of 2 minus W 2, 1, P of 1 should be equal to 0, because there is nothing else to sum over. If I set k equal to 1, I have this, and I sum over L, there is only one other value 2. And similarly you have W, well you have essentially this equation and nothing more. Okay. So this is what we call W12, and let me call this P of 2 equal to W21 P1 here. So P2 is this fellow, P2 is this, and P1 plus P2 must be equal to 1. So this must be equal to 1 minus P of 1 on this side. Okay. And what does that lead us to? It gives us explicit solutions. It says W21 over W12 plus 1 P of 1 equal to 1, or P of 1 equal to W12. W212 is a rate, transition rate to go from 2 to 1, okay. And similarly P of 2 equal to W by symmetry that is it. Those are exact solutions for the stationary distribution. Okay. Of course we also have to write the time dependent solution for P of t. We have just solved the problem W on P stationary equal to 0, and we have this. But now think about it a little bit, and you see immediately how physical this solution is, because what we have is a process, and we can now draw this, let us draw this, is a process which as a function of time it takes on two states possible. Now we need a symbol to say what the values of this random variable are, which can take two possible values. Let us call those values two constants, C1 and C2 for example. So let us say C1 is sitting somewhere here and C2 is sitting somewhere here. Then what it does is it starts in say state 1, goes on for a long time, so at any arbitrary instant of time you can put the origin of time, and then it abruptly makes a jump to C2, and then goes on for a while, it makes C1, and then it does this, etc. So this is C1 and that is C2, two states. It is a two state process, and in each state the value of the variable is either C1 or C2, okay. And it keeps switching back and forth randomly between these two states. So you can now imagine, can easily imagine how many possible situations this will model immediately. Anything which has got two possible states, either an on and an off, or or a passive state and an active state, you name it, a huge number of applications where this model will work, the simplest possible model. Now what is the rate or average rate at which it switches from one to the other? So we have already said that, we have said that W12 is what we call W12 is the rate from at which 2 to 1 switching is happening. So let us call this lambda 2, the rate at which the system switches state. If it is in state 2, the rate at which it switches to state 1, and similarly 2 1 is the rate at which it switches from 1 to 2 equal to lambda 1 say. Okay. Then according to what we have here, it says P1 must be equal to W12, that is lambda 2 over lambda 1 plus lambda 2, and P2 must be equal to lambda 1 over lambda 1 plus lambda 2. Okay. Now what is the physical meaning of this lambda 1 and lambda 2? If you look at this picture, you see that it stays, suppose it had started like this somewhere, it says stays for a time interval in state 1, random time interval, another random time interval, another random time interval, etc. And the average over all these things is the mean residence time in state 1. So if you say what is the average in between switches from state 2 to 1, in between, what is the average time it spends in each time it reaches state 1, let us call it some tau 1. So average residence in state 1, let us call it tau 1, and similarly the average duration of a stay in state 2, let us call this average equal to tau 2. Okay. Then clearly the switching rate is just the reciprocal of these things, right. So it is clear that lambda 1 tau 1 equal to 1 over lambda 1 tau 2 equal to 1 over lambda 2. So it says this time is obviously equal, this is equal to tau 1 over tau 1 plus tau 2, and this is equal to tau 2 over tau 1 plus 2. Okay. And that is exactly what you would expect physically, because now you would say, if I look at it as a function of time and I put my finger on one particular point in time, I ask what is the stationary probability that it is in state 1 or state 2? Well, the probability that it is in state 1 will be the fraction of the time that it spends in state 1 over a long period of time, and similarly for state 2, and they are precisely proportional to the mean residence time in state 1 divided by the total residence time. These are the fractions. Okay. So we have a simple physical interpretation of what is meant by the equilibrium distribution for a dichotomous Markov process. It is just the ratio of the fraction of the mean residence time in one of the states divided by the sum of the residence times in both the states. Okay. So it is physically very clear, this is what is happening out here. Okay. We still have to solve this problem of the time dependent problem, we have still not dealt with that, but the stationary distribution is completely clear in this particular case. Now even if you have a 3-state process, the formulas that you write down in general without detailed balance are not so trivial, they are quite involved, they get more and more algebraically more complicated, but when you have something like detailed balance, then of course it simplifies enormously. But the most popular model is the dichotomous Markov process in this case. Now what remains is to ask what happens as a function of time, what happens when you put in the time dependencies everywhere, and this is what happens. We need to solve this problem by going back and saying d over dt So we write the solution down. P of t is e to the wt p of 0, and we need to know what is w, and w was equal to w11, w12, but w12 was the rate to go from 2 to 1 on this side, which was lambda 2, and similarly w21 was the rate to go from 1 to 2, and the diagonal elements are minus those guys. So that is W, the transition matrix, and we need to find the exponential of this matrix. So you square it, you cube it and things like that and find out what is the exponential. But matters are made a little simpler by noticing that W squared is minus lambda 1, lambda 2, lambda 1 minus lambda 2. This is W squared, and what is that equal to? It is lambda 1 squared plus lambda 1 lambda 2. So take out the lambda 1 and you get lambda 1 into lambda 1 plus lambda 2, and then minus lambda 1 squared minus lambda 1 lambda 2. So again we take out a lambda 1 and then on the other side you get minus lambda 1 lambda 2 minus lambda 2 squared. So it is minus lambda 2 lambda 1 plus lambda 2, and then finally lambda 1 lambda 2 plus lambda 2 squared. So that is lambda 2 plus lambda 2. So we can take out the lambda 1 plus lambda 2 and write this as equal to lambda 1 plus lambda 2 times lambda 1 minus lambda 1, that is just minus of this guy out here. So this is turning out to be equal to minus and then a W itself. Okay. Now the rate to go from 1 to 2 is lambda 1 and 2 to 1 is lambda 2, and the average rate is half the sum, right. So let us define the mean transition rate. Lambda is lambda 1 plus lambda 2 over 2. Okay. So it says that W squared equal to minus 2 lambda W. That of course immediately makes the problem of finding the exponential trivial, because it says W cubed is proportional to W once again and so on and so forth. So where does it get us? It says e to the Wt is the identity matrix plus Wt plus t squared over 2 factorial W squared, which is minus 2 lambda W, and then t cubed over 3 factorial, and then W cubed, but that is W times W squared and so on. So it is minus 2 lambda whole squared W, etc. all the way. So let us write this as I plus, let us take out a W, let us take out the W, and then let us write this term as minus 2 lambda Wt divided by 2 lambda. Let's write it in that form. So this becomes over minus 2 lambda, minus 2 lambda. Take out a minus 2 lambda in this fashion, and then inside I have minus 2 lambda t plus minus 2 lambda t whole squared over 2 factorial plus dot dot dot. I took out a minus 2 lambda, so let me put that back in here so that it matches this power out here. But what is this fellow? E to the minus 2 lambda t minus 1, right. So let us erase this, 1 minus e to the minus 2 lambda t, and get rid of the minus sign. And it is over, right. Now we can write the full probability distribution down completely. I leave that to you as an exercise to write this down. So you should be able to write down P of, now let's put in the values that we have for this process. So you should be able to find P of C1 comma T, given that you started in C1, P of C2 comma T, given that you started in C1. How would you find this? What is this guy equal to? This is e to the wt on the initial matrix. And what is the initial matrix? If I start with C1, what is this equal to? It is equal to 1 at t equal, and what is this? 0. So all you have to do is to apply that to this fellow. All you need to do is to apply this matrix, which is a 2 by 2 matrix, because we know both W and I. Apply it to this fellow and read off these two numbers. And similarly, P of C1 T C2 and P of C2 T C2, this column matrix is equal to e to the wt, that is this matrix acting on 0 1, and you can write the full matrix down. Okay. By the way, just to check, since we have this statement here, if you let this, if you let t tends to infinity, if you let t tend to infinity, we better recover the values that we already had for the equilibrium distribution. What happens to this guy? It becomes a stationary distribution, P1, P2, right. So you have P1, P2 should be the limit of e to the wt on the initial state, whatever that state is, whether it is in 1 or 2, we do not care. Now what is the limit of e to the wt? You can read it off from here. Yeah, so we know that the limit t tends to infinity e to the wt turns out to be the identity matrix plus w over 2 lambda, because this goes away. So you have 1 0 0 1 plus w over 2 lambda, and now you have to tell me what is 1 over 2 lambda. What is w, by the way? It was lambda 1 here, lambda 2 here, minus lambda 1, minus lambda 2 in this fashion. Okay. Added to this guy out here. And this is lambda 1 plus lambda 2. Okay. So what does this become? Equal to lambda 1 plus lambda 2, so it is lambda 2, again a lambda 2, and then a lambda 1 and a lambda 1, 1 over 2 lambda times that. Right, on whatever initial state you want to put down. Now one of our articles of faith is that as time increases, the initial value should not matter. So whatever be the initial distribution, I should still get the equilibrium or stationary distribution to be the same thing. So whether I apply it on 0 1 or 1 0, it shouldn't matter, it shouldn't matter at all, otherwise I am in trouble, right. In fact, I could have had a of this and 1 minus a of the other. So let us do that and see what happens. So suppose the initial state, this fellow here, had been some a b with a plus b equal to 1, non-negative numbers such that a plus b is 1. So we apply it to a b, and what do you get? You get lambda 2a plus lambda 2b. So lambda 2 comes out and you have A plus B which is 1, it goes away. So this indeed gives you lambda 2 over lambda 1 plus lambda 2 and lambda 1 over lambda 1 plus lambda 2 independent of A and B. Well, independent of A. B is 1 minus A in case. So that corroborates the requirement we had that the stationary distribution should not depend on the initial distribution at all. Okay. So it does cancel out, this thing does. That is why you had the same element in both places out here. And that is exactly this is exactly the equilibrium distribution we discovered earlier. Okay. But you can write the time dependent one out here. You write this out explicitly. I leave you to do this, a little bit of algebra, but you get expressions. So what's the decay to equilibrium? What's it going like? There is a constant part in these probabilities which gives you the stationary part, and then there is a part which decays. There is only one more eigenvalue. And what's that other eigenvalue? Minus 2 lambda. So the correlation time, you expect the correlation time in this process is going to be 2 lambda inverse. And again that corroborates what we are going to find the correlation time explicitly. I am going to define it in a minute, but you see it is this time scale that is the correlation time. In a very specific way, we will see that the autocorrelation will die down with this exponent out here. But what is this guy equal to? This is equal to 1 over lambda 1 plus lambda 2, right, which in turn, remember this is, it is equal to tau 1 tau 2 over tau 1 plus tau 2, because this is 1 over tau 1, that is 1 over tau 2. And what is this number? What sort of mean is it? It is the harmonic mean of the individual residence times, right. So we have this very simple relationship which says in a dichotomous Markov process with mean residence times lambda tau 1 and tau 2 in the two states, the correlation time of this process, the time on which it loses memory in some sense, is the harmonic mean of these two individual times. Okay. Now let us define correlation. Well, some things can be written down immediately, and then we will, if time permits, do this, or I come back to this a little later. We will write the answer down, at least in equilibrium we will write the answer down. So I ask now, what is the mean value of this process? Let us call that process x. So what is the mean value of x? X has values C1 and C2. The sample space of x comprises the two values C1 and C2, and the system is switching randomly back and forth between these two values with mean residence time tau 1 and tau 2 respectively in the two states. So what you expect is the average value of x. X stationary is with respect to the stationary distribution. By definition this is equal to C1 P1 plus C2 P2 by definition. The stationary or t tending to infinity average has got to be this, because P1 P2 are the stationary probabilities and C1 C2 are the corresponding values, therefore this is the weighted average and it is a normalized probability. And what is this equal to? Not surprisingly, this is C1 tau 1 plus C2 tau 2 over tau 1 plus tau 2, or in terms of lambdas it is C1 lambda 2 plus C2 lambda 1 over lambda 1 plus lambda 2. Okay. What is the mean square going to be? Well, same guy but with squares, right. So it is C1 squared tau 1 plus C2 squared tau 2 over tau 1 plus tau 2. Again this is the stationary. And what is the variance going to be? So what's delta x, that is the difference between this and the mean squared, stationary, delta x whole squared stationary. What is that going to be? That is equal to this minus the square of this fellow. Now the square of this is, first of all, if I take this minus the square of that, there is a tau 1 plus tau 2 multiplying this fellow here. So let us quickly do that. Let us C1 squared tau 1 plus C2 squared tau 2, tau 1 plus tau 2 minus C1 squared tau 1 squared plus C2 squared tau 2 squared plus 2 C1 C2 tau 1 tau 2, the whole thing divided by tau 1 plus tau 2 squared out here. So some terms definitely cancel out. We can write down a very simple formula, and that is delta x whole squared in the stationary state is equal to, first of all, the tau 1 squared cancels with this guy, the tau 2 squared cancels with that, and then you have a C1 squared tau 1 tau 2, a C2 squared tau 1 tau 2, and then you have minus 2 C1 C2 tau 1 tau 2. So this is equal to tau 1 tau 2 right, that is it. Okay. Now what is tau 1 tau 2 over tau 1 plus tau 2? It is the correlation time, right. So there is a direct connection between this. What happens if C1 C2 equal to minus C1? Okay. This becomes a square of whatever value. So sometimes it switches between plus 1 and minus 1 or something like that, then the formulas simplify. That is called the symmetric dichotomous process. We will talk about that a little while later. But what happens if there is time dependence? So the next question to ask is the autocorrelation, the generalization of the variance, and I will do that tomorrow. We need to generalize this to ask, is delta x at any instant t1, delta x at any instant t2, what is that equal to? That generalizes the variance, but this is a stationary process. So this thing must be a function of t2 minus t1 or something. So I might as well look at delta x at any time 0 and then call this just t. What would this be? If t equal to 0, it should reduce to this, right. So it is this times something or the other, and you expect the memory is going to drop as a function of time exponentially with the correlation time, which is 2 lambda inverse. So what do you expect this formula to be? What do I expect this to be in general? That is equal to this multiplied by e power minus 2 lambda. So the dichotomous Markov process is exponentially correlated. Okay. And we will prove this. We have to define the correlation time, correlation itself, autocorrelation more precisely. We will do that, and then we will take it from this point tomorrow.